Hi everyone. In this lecture, we'll discuss about inductor and capacitor circuits, lossless LC circuits with diodes in it. Okay. So, and throughout this lecture, I'll assume that the diode is an ideal diode, meaning it can either have it has a finite V gamma, that is the cut-in voltage, and it doesn't have any associated resistance with it. So there are two possible structures for inductor and capacitor circuits with diodes in it. In the first case I've shown here is where the diode is in series with the L and C circuit elements. The second case here is where the diode comes in parallel with both L and C elements, the inductor and capacitors. The second case is more of a trivial case to solve, so I'll not be discussing problems based on this. I'll only be discussing the first case, which has some very interesting results. And I thought now that we have finished parallel and series RLC circuits, I thought before I move on to probably transformers or into a deeper analysis of second order systems, I thought I'll have a lecture on just solving problems on analyzing circuits with inductor, capacitors and diodes. So first I'll analyze this circuit wherein we have a capacitor which is initially charged say with 1 volt and it's connected through a diode to an inductor. Now first I'll also assume that the diode is an ideal diode which has a cut-in voltage which is V gamma is 0. So the IV characteristic would look something like this. So for any voltage greater than 0, the diode will start conducting. It will drop 0 volts across the diode and it can carry any amount of current. In that case, we'll see what happens in the circuit. Now, if there were no diode, if the diode was absent, then in that case, we already know that the inductor and capacitor forms a parallel LC circuit with an initial voltage of 1 volt. And the capacitor will be discharged by the inductor and the energy will be stored in the inductor. So, the waveform is going to look something like this, where we are going to get an oscillatory voltage signal across the tank, across the LC circuit. Okay. So in the first half cycle, so first your capacitor will be discharged by the inductor and the inductor current will peak. It will reach a maximum value of, if you know the voltage across it, we have already discussed this in one of the previous lectures. If you know the peak voltage or the initial voltage, in this case peak voltage will be the initial voltage divided by omega naught L, or Vp into omega naught C is going to give me the peak value of the current signal. And current and voltage will both be in 90 degrees out of phase. So when the voltage signal goes to 0, that's when all the energy stored in the capacitor is 0 and it's fully transferred to the inductor. The current in the inductor will be maximum. So current will be flowing in this direction and it will reach a peak value, and then the inductor current will now start charging the capacitor in the opposite direction. So the capacitor voltage will become negative, and when the capacitor voltage reaches a value of minus 1 volts, the current in the inductor will go to 0. It should also make sense because the energy of the capacitor is same as whether the voltage is negative, but the energy is same at this point and in this point. Okay. So therefore, since the capacitor energy is equal to the maximum energy in the system, which is half into C into 1 square, C by 2, so the energy in the inductor has to be 0. Or we can also see that the current through the inductor, the IL, I'll call it IL of t, which is given by integral 1 by L V C or VL of t dt. So if I integrate the positive half cycle of the voltage waveform, I get the current. Provided there is also a scaling factor with 1 by L, I get the peak value of the current. Similarly, for the current to go to 0, at this point, if I want to find the value at this point, I'll have to integrate the voltage waveform in this half cycle. So since it's the area under the integral will be same, the current will also go to 0. That's other way of looking at it. Now what happens after this? After this, the current is 0, but the capacitor voltage will now be minus 1. So now in this case, the capacitor voltage is going to be minus 1 volts. So now the inductor will generate a current in this direction. Will start building current in the other direction. So the direction of current will now reverse. It's going to flow like this. It's going to become negative and it will reach a negative peak and then it will go back to 0. And the cycle continues endlessly. Now we will now insert a diode in between. So when I add a diode in this circuit, so for the first half cycle, so the inductor, now that we know, I'll assume that this is ground, this is at 0 volt, so this is at 1 volt, and this node initially will be at 0 volts. So diode sees a forward bias voltage, so diode will start conducting. We have assumed V gamma equals 0 for this, so therefore the entire 1 volt will now appear across the inductor as well. So I'll plot the voltage across the inductor. So we can see that the voltage across the capacitor is nothing but the diode voltage plus the inductor voltage. VL is the inductor voltage, VD is the voltage across the diode. So since VD is 0 when it's in forward bias, so VC equals VL. So the voltage across the inductor, which is same as the capacitor, will start reducing as inductor starts discharging the capacitor, and it will store the energy in as magnetic energy. So when the voltage goes to 0, the current is going to reach a peak value. This is IL of t. And now again the voltage will go to a negative value, the other half cycle. It will reach, this is plus 1, it will reach a value of -1. At this point the current will reach 0. The current will come to 0. Now the capacitor is charged to -1 volts and the inductor current is 0. All the energy, the inductor, whatever energy it has stored, it has fully transferred it to the capacitor now. Now the current in the circuit has to reverse. If there was a flow of current in the circuit, then it has to reverse. So what would happen? You need current to flow in this direction. So that's what was happening in a normal LC circuit without any diode in it. But now we know that a diode is a device which can only let current to flow in one direction. It doesn't allow current to flow in the opposite direction. Okay, so therefore there will be no current transfer and the diode will just behave like an open circuit. The diode will now behave like an open circuit and the voltage across the capacitor will stay there forever. It will stay at -1 volts forever. So in this circuit, what we saw is that if I charge the capacitor to an initial voltage of Vx, I'm assuming the cut-in voltage of the diode V gamma is 0, it's an ideal diode. In that case, the voltage across the capacitor will start from Vx and reach -Vx and stay there forever. Okay, the voltage across the inductor, on the other hand, we saw that initially. I'll draw it in a different color. So the voltage across the inductor was same, it was following the same graph, but at this point again, if the inductor has some finite voltage across it, then there will be some current building across it, but that's not possible because the diode becomes open circuit after some time. So the voltage across the inductor will suddenly go to 0 and the current in the circuit started from 0, reached a peak value, and then it returned back to 0 at this point. So at this point all the energy is stored in the capacitor, okay, and that's energy is C by 2, half C into 1 square, Vx square, sorry. In this case, since I've assumed it is Vx, so it's going to be half C into Vx square. So that will be the energy stored in the capacitor, but now the polarity of the voltage is reversed. So similarly, when I connect a diode in the opposite direction, if I have a positive voltage across the capacitor, if I have a positive voltage, then current has to flow. Normally current had to flow in this direction in the circuit, but that's not going to be possible. So what will happen is that the voltage Vx will stay as it is. Okay, so I just forgot to mention in the previous problem as well. If I began, in case the previous problem had an inductor and diode connected this way. So if the capacitor voltage was negative to begin with, if it was initially charged to a negative voltage, the diode will act like an open circuit and the voltage across the capacitor will always stay at -Vx. Okay, it will always be at -Vx. So similarly, if I just reverse the diode, the voltage across the capacitor will always stay at Vx volts. If I apply a negative voltage, or if I charge the capacitor to a negative voltage minus Vx, so then in that case there will be a current flow in this direction. The same thing will what we discussed for the previous problem with the polarity of the diode. Similar thing would happen here as well. The inductor voltage or the capacitor voltage will start from minus Vx, reach 0, the current in the circuit will reach a peak value, and then it will reach a maximum value of plus Vx. At this point the circuit will come to something like this. So you will have a capacitor would have stored a positive voltage across it, there will be plus Vx. Now the diode will just open up and the voltage across the capacitor will remain constant. Okay, so by adding a diode, what we did was that the circuit was only operating for 1/2 cycle when the current was actually flowing in only one direction in the circuit. Okay, this is happening because of the presence of diode. So we know diode doesn't allow currents in either directions, it will only allow current in one direction. So now we will analyze the same circuit, the diode and an inductor and capacitor circuit, with diode having a finite cut-in voltage. So let's say I start with 1 volt and I'll assume the cut-in voltage of the diode is 0.5 volts. Now what happens to this circuit? So in this circuit, so first we know that the diode is going to be discharged, the same process would happen, but now the difference is that 0.5 volts drops across the diode. So the IV characteristic of the diode is going to look something like this. When your V gamma is 0.5, after V gamma the diode will start conducting. So which means the diode at least needs 0.5 volts across it for it to conduct. So first the voltage across the capacitor, I will plot the voltage across the inductor. So first this is at 1 volt and this is at 0 volts initially to begin with. So the diode is forward biased. The voltage across the inductor is going to be 0.5 volts less than the voltage across the capacitor. So it will start with plus 0.5 volts and then the inductor current will start building, the voltage across the inductor will start reducing. So the inductor current will start reaching a peak value. Okay, we can do the same analysis, but now it starts with 0.5. The voltage seen by the inductor is only 0.5 volts. That will determine the current in the circuit. Okay, it's the inductor voltage across it, it's going to determine the current across it, current through the inductor. At this point, when the inductor voltage becomes 0, the voltage across the capacitor is 0.5. So the diode will drop all the voltage across it. So this is 0.5 volts. And this has completely dropped the 0.5 volts across it, and the inductor voltage is 0. But the inductor current has reached a peak value. So the current will keep flowing in the circuit further. Okay. So normally if the inductor had, let's say we charge the inductor using a switch in this fashion, I have charged it, I've let an initial current, I've set an initial current in the inductor using a switch, and for a long time the switch is closed. At t equal to 0, the switch is suddenly opened. So when the switch is suddenly opened, the inductor has to lose all this energy suddenly. So then we know that it will develop an impulse of voltage across it. EMF impulse of voltage will induce across it, and it will lose all the current instantly. That is, if it has no other path, if it's completely open circuit, then it will do that. Otherwise, the inductor will look for whatever path is available. So for example, in this case, when it comes to 0 volts, the current has to flow in the circuit. So what will happen is that this node voltage will become negative. The voltage shown here, this node voltage, the voltage across the inductor will become negative. Okay, so the diode is still forward biased. Even though the voltage across the capacitor is reducing, the voltage across the inductor can be negative and the diode can be forward biased. So current can keep still flowing in this direction. So the current will reduce, but the direction is not changing yet, and the voltage across the inductor will reach a value of minus 0.5 when the current becomes 0. Okay, again this follows from the area under this equals to the area under this when the current becomes to 0. It took 1/4 of a cycle to build this current, so it will take 1 more quarter of a cycle to lose this current. So that's the way you can look at it. Now this inductor voltage has reached a value of minus 0.5. At this point, if you look at it, the current through the inductor is 0. So I'll draw the circuit at the end of one half cycle. Now the capacitor voltage is 0 volts. There is a 0.5 volt drop across this. Now the current has also become 0 in the circuit. Okay. So I'll also plot the voltage across the capacitor. The voltage across the capacitor is simply the voltage across the inductor plus 0.5. So it will start from 1. It will start from 1 and then go to 0 at this point. So when you look at it at the half cycle, at the end of this half cycle, we can see that both the inductor current and the capacitor voltage come to 0, which means the energy in the circuit is 0. So when there is no energy in the circuit, there will be no oscillations after that. So the capacitor voltage goes to 0. So the capacitor voltage starts from 1, goes to 0.5, then to 0 at the end of one half cycle, and after that it will remain at 0. The inductor current, if you see, it reached a peak value at this point and it reached 0 again and it will stay there. Okay. So after this, the circuit comes to rest. Both the and what will happen to the inductor voltage is that the inductor voltage first started from plus 0.5, it reached minus 0.5. Now there is no other energy element in the circuit, to drive the current or to drive the either to increase the voltage or to increase the current. Okay, there is no possibility. So suddenly the inductor current voltage will come to 0 volts. See, the voltage across the inductor can change instantaneously. Okay, and neither the current in the loop or the current in the across the inductor will not change instantaneously. But the voltage can have finite instantaneous changes without any increment in the current. So the only possible solution is, again, the voltage across the inductor cannot stay at minus 0.5 because otherwise it will start building current in it. That's not possible now. Okay, because for the inductor to build current, someone has to provide energy to it. On its own, when it starts from 0 current, it can't build a current. So the voltage across the inductor will also come to 0. So now where did this energy go? Where did this energy? We had an initial energy of half C into 1 square, which was C by 2 joules of energy. But then where did that energy go? So that we by now can see that it gets dissipated across the diode. So now the diode model, where we assume that the model for the diode is something like this. So for any voltage greater than V gamma, it can conduct it can conduct any amount of current with just a voltage of V gamma across it. So here we have modeled the diode as a voltage source of value V gamma, but we know a diode can carry current only in one direction. Current can only flow from positive to negative terminal. So which means the diode will always absorb power or dissipate. I can also say it will always dissipate power. Okay, so that's where the power gets dissipated. So you can actually very easily prove that what is the power dissipated. So, if you know the current in the circuit, you can find the power. So the current in the circuit can be found by, so the peak voltage appearing across the inductor is 0.5 divided by omega naught L is the peak current value. That into sine omega naught t will be the current waveform. So this you will have to multiply it by V gamma. In this case it is half volt. So this is the instantaneous power dissipation, power dissipated across the diode. To find the energy, I will have to simply integrate it for one half cycle. Okay, it has to go from 0 to T by 2. So the waveform is something like this. Okay, so then I will have to integrate it from 0 to T by 2. So this will reduce from omega naught L and you would get cos omega naught T with a minus sign. The integral going from 0 till T by 2 can also be written as pi by omega naught. Okay, omega naught is 2 pi by T. It comes from that. Okay, so from this result we can see this there is also a by omega naught here, and I can write this 1 by omega naught L as omega naught into C. Okay, so this result is 2 by omega naught, and you'd get half and 2 cancels out, you'd get C by 2. So this energy gets completely dissipated across the diode. Okay, so now does it happen always? Does the voltage always come to 0? No, it actually depends upon the value of V gamma that we have chosen for the diode. So for example, if I assume that the V gamma instead of 0.5, if I assume that it is 0.2 and I'll start from 1 volt, then we know that in the positive half cycle, the diode, the voltage across the inductor is going to be 0.8 volts. I mean, this is 1, and the inductor voltage is going to go from plus 0.8 to 0 and then 0 to minus 0.8. So when the inductor voltage goes to minus 0.8, the voltage across the capacitor is going to be, so you will drop 0.2 volts across this. So the voltage across the diode is going to be minus 0.6. Sorry, the voltage across the capacitor is going to be minus 0.6. So this is minus 0.8. Okay. So the voltage across the inductor, it will go to minus 0.8. At that time, the capacitor voltage is going to be minus 0.6. So it will start from 1. I mean, I plotted this 0.8 to minus 0.8, assuming that, we have already done this analysis for one half cycle. The current will reach a peak and it will go to 0 at this point. So from that we get plus minus 0.8. And the inductor capacitor voltage is simply you just add 0.2 to the inductor voltage, you get the capacitor voltage. It will start from 1 and then go to minus 0.6. And once it reaches minus 0.6, at this point we know that the capacitor voltage will stay at minus 0.6, because the after this the current direction has to reverse, but that's not going to be possible here. So therefore it will stay at minus 0.6 forever. So if I assume any general V gamma, and then I start from an initial condition of Vx across this, then the voltage across the capacitor will start from Vx, or I can plot first the voltage across the inductor. It will start from Vx minus V gamma, it will go to 0 and then it will eventually go to a negative value of this, so it will be minus of Vx minus V gamma. Okay. So now to plot the capacitor voltage, I will have to just shift this by V gamma. So you will start from Vx and go to a negative value. So it will be minus Vx plus 2 V gamma. So I will simply write it as minus of Vx minus 2 V gamma. So in the previous problem, Vx was 1 and V gamma was 0.2. So 1 minus 0.4. So you get minus 0.6. Okay. After this, it will remain constant. Now we can exactly show that the initial energy in the system was, the capacitor stored was half C Vx square. The final energy that the capacitor is going to store is half C into Vx minus 2 V gamma the whole square. Okay. Now the remaining energy will be lost across the diode. Okay, you can simply find the difference between these two energies will be the energy that's lost across the diode. So in the first problem, when we analyzed for this circuit, we assumed V gamma in one of the second case, V gamma as 0.5 and Vx as 1 volts. We started from there. So that's why we got this value Vx minus 2 V gamma was 0. For that special case it was 0. That's why the system came to rest. Capacitor voltage became 0, the inductor current became 0. But that need not be the case. It depends on the value of Vx and V gamma. Vx here is the initial voltage and V gamma is the cut-in voltage. So now the next circuit is, we'll introduce now two diodes connected back to back in parallel and shown in this way, and see what happens to this circuit. So for the first case, I'll assume that the cut-in voltages of the diode is 0. Both the diodes is 0. In that case, if I just take this composite combination of two connected back to back connected two diodes connected in parallel by the terminals reversed, then the IV characteristics of this would look something like this. So when you apply a positive voltage across this, say when I'm applying any slightly positive voltage across this diode will conduct. For a negative voltage, this diode will conduct. So the characteristic would look something like this. So for a 0 V gamma, you can have current in both the directions. So current can flow in this direction or this direction. This is the IV characteristic, current versus voltage. Okay. And this is nothing but, if you remember from the previous lectures, This is nothing but the IV characteristic of a short circuit or a 0 volt DC source. A 0 volt DC source can carry current in either direction and still always maintain 0 volts across it. So that's simply equivalent to replacing this by a short circuit. Okay, if I apply a voltage Vx, initial voltage Vx across the capacitor, this will exactly behave like a simple parallel LC circuit with the voltage across the capacitor oscillating between plus Vx and minus Vx with the frequency omega naught given by 1 by root LC. Okay. Now here, of course, diodes are carrying current, but now the thing is that the voltage across the diode is 0. The V gamma is 0. So which means the power dissipated across the diode is 0. So they will behave like lossless elements here. So only when the diode has a finite V gamma, then there will be a power dissipation across the diodes. And now the second case is when we will assume the diodes have a finite V gamma. So I am going to assume the diodes having a finite V gamma. So in that case, if your V is greater than V gamma, then this diode will conduct. If your voltage across this is less than minus V gamma, then this diode will conduct. Okay. So the IV characteristic would look something like this. So for any voltage greater than V gamma, there will be conduction, and any voltage less than minus V gamma, again there will be conduction. So this is I and V. So in that case, we will see what happens to this parallel LC circuit. So now I have two diodes connected back to back in parallel. So if I start with say, and I'll start with some numbers here. So if I start with say 1 volt, and I can assume the diode having 0.5 volts cut-in voltage across it, but then we have already solved that problem. I can start with a case where this is 0.5 volts, assume V gamma is 0.5. We already solved it. By the time it just completes one reference cycle, one half of the oscillation cycle, the current will return to 0. The voltage across the inductor will go from plus 0.5 to minus 0.5. And the voltage across the capacitor will go from 1 to 0. We already discussed this problem. Okay. So the system will come to rest at one half of the oscillation cycle. So we'll analyze for a different case. I'll start with V gamma as 0.2. I'll assume V gamma as 0.2 volts. When you assume a V gamma of 0.2 volts, so again the inductor is going to carry the voltage across the inductor is going to be plus 0.8, and again in the other half cycle it will go to, in the other quarter cycle it will go to minus 0.8 volts, and the current in the inductor is going to reach a peak value at when the voltage across the inductor is 0, and it will reach 0 when the voltage across the inductor is minus 0.8. Now when the voltage across the inductor is minus 0.8, we know that the voltage across the capacitor is minus 0.6 volts. So because this was the diode which was conducting, the upper diode was cut off because that cannot take current in, because previously the current flow was in this direction. Okay. At the end of this cycle, the capacitor voltage came to, from 1 volt it came to minus 0.6. Now, but the direction of current was like this. Now we can see here the direction of current has to reverse. So we know that this diode can no longer conduct, this diode can no longer conduct. So if there is any current conduction, it has to happen through, it actually has to happen through the other diode, which is this. The current has to flow through this diode, this way. So now if this is at minus 0.6, and if you spend 0.2 volts across this, then the voltage across the inductor will suddenly become minus 0.4 volts. So remember, the voltage across the inductor can change suddenly. Capacitor voltage will not change suddenly. Okay. And similarly, the current through a capacitor can change instantaneously, but not the voltage. Okay. So using these two facts, we can analyze this. But since both the circuits are in series, both the circuit elements are in series, we can't say that the current can change instantaneously, because both the current is the same variable for all the elements here, but voltage across the capacitor and inductor they are separated by the diode, so they can change. The inductor voltage can change instantaneously. And we also know, even if the inductor voltage change instantaneously, there won't be any sudden changes in the current. Okay, and for the current to flow, for the direction of current to reverse, the voltage across the inductor will suddenly come to, so it started from, I'll draw it again, it started from plus 0.8 and then it reached minus 0.8, and then suddenly it will come to minus 0.4. Again, from minus 0.4 it will raise and go to plus 0.4. The same logic continues. So wherein now the direction of current is reversed. So I'll draw the current in a different color. So the direction of current is reversed. So it will reach a less peak value because the voltage, the initial voltage across the inductor is minus 0.4 now to begin with. It will reach a value, the peak value will be slightly smaller. At this point it will again come to 0. Now the voltage across the inductor is plus 0.4 volts. Okay, so the voltage across the capacitor, the direction of flow of current is in this way now, it's reversed. So this is plus 0.4 volts and the voltage across the capacitor is going to be plus 0.2 volts. Now when the diode voltage, the capacitor voltage comes to plus 0.2 volts, now again the direction of the current has to reverse. It has to now flow in the opposite direction. Okay, the direction of current has to reverse. For the direction of current to reverse, the only path it can take through is through the diode. Okay, so the voltage across the inductor can change suddenly. I mean, there is no such thing there. The voltage across the current can, the voltage across the inductor can change suddenly. So for the inductor to carry current in the opposite direction, this diode has to be turned on, but it needs 0.2 volts across it for it to conduct. So the entire voltage stored across the capacitor will drop across the inductor. And when it does, the drop across the diode, the voltage across the capacitor will entirely drop across the diode. The voltage across the inductor is going to be 0 volts. So therefore it will have no energy, no current built in it, because the voltage is 0 to start with. The initial, the current at this point, at the end of one cycle, is 0 now. So it will not build any extra current. So the circuit, or I can say that the diode will just not carry any more current. So it will be like an open switch. Okay, so the capacitor voltage will stay at 0.2. So now what happened, if I draw the waveform across the capacitor, the first cycle it went from plus 1 to minus 0.6, and in the next cycle it went from minus 0.6 to plus 0.2. Okay, and then stayed here. So just to draw, in case if there was no attenuations, it started from 1 volt. If there was no diodes, if there were no diodes, then it would have simply kept oscillating between plus 1 to minus 1 like this. But because of the losses in the diode, every half cycle it's going to lose some energy. Okay, so every half cycle each diode is going to conduct. So every time a diode conducts, it's going to dissipate some power, or therefore it's going to dissipate some energy as well. So to generalize this, we can very easily show that if I assume a finite V gamma for assuming both the diodes have same V gamma, then if you start from an initial voltage of Vx across the capacitor, so I am going to assume the case where we have two diodes connected in parallel. If I start from an initial voltage of Vx and assume the cut-in voltage for the diodes to be same and equal to V gamma, then the voltage across the capacitor will go from Vx to minus of Vx minus 2 V gamma in the one cycle, and in the other cycle it's going to lose 2 V gamma further. It's again going to come to Vx minus 4 V gamma. Okay, and after that it will remain, it depends. So it depends on the value of V gamma. So what will happen is that, so we know that the diodes, for the diode IV character, the combination of the two diode combination IV characteristic looks something like this. If the voltage across the capacitor is in this range, then there will be conduction. Okay, if the voltage comes to this range between minus V gamma to plus V gamma, then there will be no conduction. So finally the operating point is going to come, the capacitor voltage will settle to a point where it will come to a value between minus V gamma to plus V gamma. In one case, in one special case, we assumed V gamma as 0.5 volts. In that case, it directly came to 0. So that also lies comfortably within this range, minus V gamma to plus V gamma. Okay, so that's all about the circuits that we analyzed so far. The inductor circuit, inductor and capacitor circuits with diodes. Okay, so I think I'll move on to transformers and second order circuits in the coming lectures. I'll stop at this point.